How are you guys? Welcome once more on in my YouTube channel. Today we'll be dealing with strain in a single cylinder. Obviously, you're under thick cylinders if you know, but we'll focus on a single cylinder. So I want us to check longitudinal stress. We've checked. We'll check. As you can see, longitudinal stress. Uh, that is the formula for calculating. Okay, this is 14 cylinder. This one is 14. Oh, sorry about that. This one is 14. So far, we don't use tin. We are not focusing on tin. Um, Define thick cylinder. Oh, that it is there. The definition. We've discussed about this. Um, I want us actually I want us to look at this to look at 1.1.5 Poise ratio. The Poise ratio. If a thick rubber band is stretched, the material gets thin as it gets closer. Fine. This happens most materials. Conversely, if a material is compressed, it will start to get thicker as it shortens. Fine, we know that. Um, in addition to the deformation of material, the direction of applied force has a certain amount of lateral or transversal expansion or contraction taken place at right angle to the applied force. This ratio of the lateral strain to axial strain is known as Poisson ratio. As we see in figure 1.3. We have given there, as you can see, lateral strain, original size, final size, yeah, longitudinal strain. You can see they've applied the force. You see the original was like that. They pulled that as they applied. They find that final size. As you can see, we have that object, no problem. So lateral shrinkage due to longitudinal force. There's a lateral shrinkage, as you can see. Where so how to calculate poise? The formula is the lateral strain and the axial strain. Lateral strain over axial strain. Okay, yeah, that is it. Yes, but let me tell you, you'll be given in 611, you'll be given the poise ratio most of the time. If they say you calculate it, actually, most of the time you won't use this formula. You won't be using this formula. You'll be calculating from these formulas. Here it is. You'll be making it the subject of formula from these formulas. If they ask you, but it is rare. It's very rare for them to ask you Poisson ratio. Yeah, it's very rare. But then, yeah. As you can see, says calculating the three strain acting on the cylinder. Okay, it's fine. Calculate the following longitudinal strain. Okay, longitudinal strain. The longitudinal strain is equal to the longitudinal strain, neither minus or plus the two strain. First multiply each and what we'll see this radial strain and what is it definition. Now let us check. Let us check the formulas. What is important? The three strain acting on a cylinder. Three strain acting on a cylinder. Let's check the formula for calculating strain in a cylinder. We have longitudinal strain. You see there, longitudinal strain is that. Remember, there is also radial longitudinal stress, but now focusing on strain, not stress. Longitudinal strain, as you can see, is 1 over E into that long minus V into E obvious is Young modulus of elasticity. Poise ratio, this one is Poise ratio over hoop stress plus radial stress. You see this? So what you must, those formulas here. There's a longitudinal strain, radial strain, and hoop stress. We have three strain. We have longitudinal, radial. We're talking about strain. We have longitudinal strain, and we have radial strain. We have hoop strain, right? Longitudinal strain, hoop strain, like that. So you see the formula goes like, if you want longitudinal strain, you'll start by longitudinal stress, then you see you'll have hoop stress, you add hoop stress and radial stress. Then if you want radial stress, you'll start by writing the radial stress. Then remember, you minus pause, always this minus there. Then you'll add what we have. You'll add, remember we have started with longitudinal, this is the corresponding. However, what you'll multiply by pause supposed to be the remainings. The remaining will be hook stress and the radial already, because the longitudinal have stated here will correspond like that. The remainings will be longitudinal and hoop stress. This will correspond, the remaining will be longitudinal and radial. You just can see those formulas, guys. Supposed to know these formulas, right? So yeah, stress, all those things, you have to know those formulas. So how can you apply those formulas? For example 1.5, how can we apply, let me one of the formulas, how do you actually apply that formula? So we've given example there, 1.5. So says a higher pressure cylinder with internal diameter. We've given internal diameter, and the external diameter must withstand the internal pressure of that. Oh, that's it. So take note, guys. Now we have given internal pressure. What comes in your mind? Internal pressure. When you have given internal pressure, what is coming in my mind? I know coming a stress distribution graph for internal pressure stress distribution graph, right? We've given, and then we know that is our cylinder. I've discussed about this if you have watched my video. Here's your that thing there. Here we have your diameter there, 0.25, or that okay is x. You have the internal there, which is 0. Here's your cylinder, 0.25 meter. Here you have 0.35 meter, right? There's the internal pressure. The acting, I will indicate it there with green. That is an internal pressure acting that area. Indicate your internal pressure like that. Then I said internal pressure, radial stress acting in the same direction as the radial stress is the internal pressure. Hopefully you will know that. So yeah, it is what in. So okay, let me make this big enough so that you'll understand. We have the internal pressure acting there. That is internal. Then here radial stress will act in this wall, will act in the same direction as the pressure, as the internal pressure, remember. Those arrow represent radial. We have radial, or let me leave it with red, or I can show them here. Radial stress is acting. You can see those areas, those radial acting in the same direction as this. So yeah, this is a radial, this is the internal pressure. So guys, our internal diameter there we've given to be 0, watt, 225 there. Remember, I convert it to be in meter. 350 divided by 1000 would be 0.353 meter. This is what we have, but you must know that always internal pressure or external pressure will act in the same direction as the radial stress. So the radial stress will simply equals to internal pressure. They are acting in the same direction, so they'll be equal. You must know this. Even if you're given the radial stress, you must know also is equal to external pressure. They're acting, but now here will be at what? At the outer diameter. Here, when you're given internal in the internal diameter, at the external diameter. These are just notes you're supposed to know at the internal diameter. All right, this is what we know. So that is what we've given. So since it's the internal pressure, let's draw internal pressure stress distribution graph. Hope you know stress distribution graph goes like this. For internal, I've discussed this many times. Remember, here we have internal diameter, which is 0.25 meter. Here we have external diameter 0.35 meter. Yeah, this vertical line represent diameters. So okay, can make a dot here, goes like this. Note this is a, remember, note this is a radial. Simply what, oh, let me not write this. This is a radial stress, it is negative. Remember, radial stress, it is negative, right? You have negative, then the hoop stress will be like that. Then we'll have some hoop stress there, won't reach 0. The radial stress in the external diameter is equal to 0 always, but the hoop stress cannot equals to 0, right? So here hoop stress is positive. This one represents the hoop stress. The hook stress, this is for the radial stress. So yeah, this is the internal pressure stress distribution graph. Nevertheless, here we'll have 0, do not forget 0. Let's check what are we given. The internal pressure, say the radial stress is equal to the internal pressure in the internal what? Diameter. We know that here we have internal pressure. Internal pressure is acting in the internal diameter, so will be negative. You will have negative 15 megapascal. Right. So yeah, says here calculate the longitudinal, radial, hoop strains for the cylinder at inside diameter. Note at inside, not at outside. We have given E, which E it is Young's modulus, and Poisson ratio. We've given a Poisson ratio. So yeah. So for us, they say we should calculate the longitudinal and the radial, all those things. All those things. You know what is limiting us? We know the formulas here. Here are the formulas. To calculate longitudinal strain, we'll have to have Hooke stress, radial stress. The limiting is these guys. Supposed to calculate them. And then to calculate these guys, obvious, we had no other choice. We're supposed to use that formulas. Remember, Hooke stress is equals to A plus B over D squared, outside time over D squared, depend on the diameter. The radial would be A minus B over D squared. So yeah, we are forced to start by calculating the value of what? Well, we have to calculate the value of A and B. So we had no choice. So that is why we'll have to do this. So fine, without wasting the time, let's see how Kubic trembles. Okay, I've said now you can tell the examiner we are working with add. I can set add diameter. You can tell it add diameter. Working at diameter with D is equals to 0.25. What I'm doing should 25 meter, which is the internal diameter. We are telling the examiner, you know, I'm working here. So we're just telling the examiner. Then come, what do we know about radial stress at diameter 0.25? The radial we're given them, which is we know. Remember, working at this diameter, we're working at this diameter, we take it step or still under this diameter. We've given the pressure there, which is negative 15 megapascal. It's negative 15 times 10 to the power of 6. That is our Pascal is like this, or you can write it as it is. No problem, megapascal. We have given a radial stress. We know this is at this diameter 0.25. So yeah, then we can go about. We know that radial stress 0.25 simply we know this is A radial minus B over D squared. So yes, so but we have our radial there at that diameter. We know that is minus 15 times 10 to the power of 6. A we don't know, the value of B we don't know, but the diameter is 0.25. We square it, right? Square that, or we can simply say equation 1, or we can punch this on your calculator. It's 1 over 0.25 squared. It's up to you which method you prefer. Let's make it. So this I can say that is equation 1. Now we come to tell the examiner we are done with diameter. Internal diameter, we don't know the Hooke stress, there's nothing we can do. We're done with this information. Let's go to the external diameter. Now you at external diameter, whereby it is D is equal to 0.35 meter. So these guys, they will know, okay, now this guys is not freestyling. Actually, you tell the examiner so that you will know you're working on which diameter. Then you can say the radial, what you know there. So far we know that the radial, if you like, you can write it like this, there, your diameter, like this if you want. The diameter there, the radial there at 0.35 is simply equals to 0. As you can check, this yellow point is at 0 there. So yeah, you must know that the hook stress there will be 0 megapascal always when you're dealing with the internal pressure. So yeah, we know that this is equals to 0 megapascal. Remember, it is our diameter. So yeah, but what about this? Know the equation of that. Now you come radial is equals to A minus B over D squared. So you substitute your things here. Radial is 0. A we don't know. B we don't know. Okay, let me just write it here. Radial, it will be what? Will be 0. A we don't know. B we don't know. But the diameter will be 0.35. You square that. Then you can take this to the other side. I'll simply have A to be equals to positive B over 0.35 squared. Right. So I can call this equation 2. Then I can say substitute. Now I can say substitute equation. We have to substitute equation 2 into equation 1. Right. That is what we have there. Then what is equation 1? We have our equation 1 here. So we can do our things now. Here we have minus 15 times 10 to the power of 6. But let's substitute A with its value. Where we see A, we'll replace A with this guy here. That is A with that guy. Here it's our A. If we can take A, yeah, there it's A. Then minus B over 2. Yeah. So we must be very careful here. Here we have 115 times 10 to the power of 6. So this is the same as 1 over 3/5 squared, right? You understand? I'm just taking out I can take out B as a common factor. I want you to be smart there. Be smart. Let me just say, let me take out B as a common factor. We have B both sides, isn't it? If I take out B, I'll be left with 1 over 0.35 squared minus 1 over 0.25 squared. This is how cookie crumbles. So punch what is inside there, right? Then, or that is how cookie crumbles there. You can punch that and divide by the answer. If you punch that and divide by that answer, you'll find that B is equals to 1,914 times 10 to the power of 6. It has no SI units. And we'll punch this, then you divide by the answer that you'll get there. The values that will get both sides will be negative something. You divide, find B by itself. Right. It's fine. So this is what we have. Now what about the value of A? Want the value of A? Remember, A is this one. Is this guy here. If you remember, we made A the subject and then we got A to be. This is our A value. So you can find A. A, when we see B, B is 1,914 times 10 to the power 6 divided by 0.35 squared. Then found the value of A by punching this. And get that A to be equals to 15, 625 times 10 to the power of 6. That's the value of B, of A. Right. So we have this now. Now we can find our radial and our Hooke's stresses now. You can see the radial stress at diameter, or you can say Hooke's stress if you want. I can say, okay, Hooke's stress at diameter 250 millimeter, okay, say 0.5. You can say 0.25, it's one the same thing. 0.25, right? Know this is A minus B over D squared, the formula. The value of A, we simply call it now. It is 15 times 15, comma 625 times 10 to the power of 6 minus what is B? There it's B, 19,194 is 1, not 19, 1,914 times 10 to the power of 6. Right. Then we divide this by the diameter, which is 0.25. We square it. Do not forget to square. Remember that it's our diameter. Then we punch this. What is our Hooke's stress? That 0.25 diameter. what is the Hooke stress? 46, 25 megapascal. Since it's positive, is tensile. Positive values become tensile. Right, so yeah, you have your Hooke stress, isn't it? So this is how cookie crumbles. You have this guy, your Hooke stress. Right. So what did the question say? Should calculate what? Calculate the longitudinal. They want the longitudinal and the radial and the longitudinal and the radial and the Hooke strain for the cylinder in the inside, focusing on the inside diameter. Oh, it's fine. It's nice because in the inside diameter we already given the pressure is equal to the radial. We have the radial. We already have the radial, which is negative 15. So we can attack this question and calculate what they want. We can start by finding our longitudinal stress. We said we should find the longitudinal stress. The formula for longitudinal stress, do not forget, is pressure, internal pressure, multiplied by d squared internal diameter into d squared minus d squared, which this is a external diameter minus internal diameter squared. So let's put internal pressure is the same as the we've given there, which was 15 times 10 to the power of 6. But it is 15 if it is the internal, but if it is radial, will be negative. We'll take that as negative, but now as a pressure, we'll take it as positive. Multiply by internal diameter, we know it was 0.25 squared minus external diameter was 0.35, or let me just say squared minus internal, which is 0.25 squared. So simply punch these guys, you'll get that your longitudinal stress to be equal to 15,625 megapascal. This is your longitudinal. So we have our longitudinal then. So what else do we have to calculate? They said we are done with longitudinal. They say longitudinal. They've pleased us to calculate the longitudinal stress, right? And Hooke strain for the cylinder. For argument's sake, will be in need. Okay, let us calculate. Let's just calculate. You see, they did not want the longitudinal strain. They just wanted the longitudinal stress. We have the radial. We did. I want us to calculate these three things here. What we know, okay, is fine. We did this. Let us go and indulge strain. Let me say longitudinal strain. Right. Now I want us to calculate longitudinal strain. I've said the formula of this is 1 over E, right? Remember, into radial stress. Yeah, it cannot be radial, will be longitudinal. Remember, there must be correspondings first there of the so the longitudinal stress minus the Poisson voice ratio into, you know how cookies crumbles, radial plus, without looking there at the formulas. I know this will be hook. This is how cookie crumbles. So do you know this? So yeah, guys, now let us find our nicely. We have 1 over what was in. Are we given? Yes. Check. This was 200 gigapascal. Poise ratio is 0.3. Okay, it's fine. We'll come 200 times 10 to the power of 9. Remember that was giga into all of these. We did calculate there our nicely longitudinal. We said is 15,62. Right, is 0.62 there. 5. Do you see? I did not say times 10 to the power of -6. You see, I just wrote. I did not convert this. So please let your final answer be convected. It's one and the same to convert it, because I've converted this one. Okay, the SI unit is not the same. Converted this same is times 10 to the power of what? 6. Okay, minus Poise ratio is 0.6, isn't it? Is 0.3. I don't remember. Or 0.3. Poise ratio, it is 0.3 there. Now what about radial stress? Yes, that is why we've calculated those radial stress. Remember, dealing with internal, and that we found that we have given, which is the same as radial stress, the same as internal, it's the same as internal pressure, right? Hopefully you still remember that, isn't it? So that was -15, or was -15 times 10 to the power of 6. Remember, it's make up my plus what now? Let me reduce this a bit so that I will have a space. So times 10 to the power of 6 plus the hook stress. What is the hook stress? We have calculated it. Here it was a hook stress for 46,25 megapascal. 46,25 times 10 to the power of 6. So this is how it goes. Punch this. If you punch all of that in your calculator, you'll find this longitudinal strain to be equals to 31,25 times 10 to the power of -6. Longitudinal strain has no SI units. Do not forget strain. This is a strain. Do not make mistake. It has no SI units. We have discussed about that. That strain has no SI units. You know, strain has no SI units from N5. Remember, you still remember that strain is change in length over original length, whereby it's measured in meter. Strain actually has no SI units. It's a ratio. So we have the strain Then again we should find the radial strain. Let's find the radial strain. We know this is 1 over E into radial minus that will be into radial, not radial, but will be Hooke's stress. I know this, Hooke's stress plus longitudinal. We know this by head. These formulas, I know them by brain, by head. So yeah, this must correspond there. I know 1 over 2, remember that was 200 gigapascal, whereby will be times 10 to the power of 9 into radial, it was minus 15 times 10 to the power of 6. Poise ratio, it is 0.3, right, into now Hooke's stress, it was 46.25. Can I reduce this a little bit? Times 10 to the power of 6 plus, if we did calculate the longitudinal stress, there is 15.625. 15.625 times 10 to the power of 6 into like that. So this is how it goes. Plug all these on your canvas calculator. You're supposed to get that. The radial strain will be equal to minus 167.8125 times 10 to the minus 6. There's no SI units. So then the last one, we know that obviously they said Hooke, the radial Hooke's, the radial Hooke's, the Hooke strain 1 over E to Hooke's stress minus Poise, know this by heart, will be into radial plus Hooke longitudinal. We know this by heart. Know this by heart. Not a matter of taking chances there. So yeah, that is the formula. Let me just put this bracket nicely and well. Let me just put this bracket nicely and well. So this is what it is. So radial strain 1 over, this is 200 times 10 to the power of 9 into Hooke. We know the Hooke stress is 26. The one that we've calculated previously, we know this, times 10 power of 6 minus 0.3 Poise ratio into radial, which was what, 15 is negative 15. Remember, negative 15 times 10 to the power of 6 plus 15,625 times 10 to the power of 6. Then the brackets there is power of 6. Do not be hopeful. As you plug these, you'll get that the Hooke's train will be simply 230,3125 times 10 to the negative 6. So it has no SI unit. So this is how then you go about applying these formulas. You see, I've applied these formulas 1, 2, 3. Yeah, this is how you go about, but we're focusing on the inside diameter, which is the internal diameter. So nevertheless, thank you guys for watching, and please do not forget to subscribe to my YouTube channel and share this to your fellow classmates. Like and comment. All the best.